Assalamualaikum warahmatullahi wabarakatuh. Good morning. Today I will explain about the part 2 of power amplifier. After we learn about the series fit class A amplifier, then we will study about the transformer couple class A amplifier. Okay, so you can see the differences between the transformer couple class A amplifier and then a series fit is we have the transformer over there. So the transformer replace the load resistor. As you can see in the series fit, the load is the RC here. This is the load, and then we replace it with the transformer. And then the secondary turn of the transformer is connected to the load resistor. So this is the load resistor, RL. This is the load. Okay, so the circuit use the transformer to couple the load. It will be improve the efficiency of the class A to 50%. And okay, a transformer can improve the efficiency because it's able to transform the voltage, current, and impedance, as you can see. And I think you already learned about the transformer. They can transform the voltage from the primary turn to the secondary turn. So we can see if we have the different turn between the first, this is the first turn or the primary turn, and then the secondary turn, we have the N1 and N2. So the voltage ratio between two coupled transformer is the V2 per V1 is equal to N2 per N1. And then about the current ratio, I2 per I1 is equal to N1 per N2. Then we can, from the voltage ratio and the impedance ratio, we can calculate the impedance ratio. The impedance ratio is R accent L, so the impedance in the transformer per the load resistor. This is the load resistor. So this is the transformations impedance, and then this is the load. This is the real impedance, real load impedance is equal to R1 per R2 is equal to N1 per N2 square. So this is the impedance transformations, and then we replace N1 per N2 become A, so A quadrat. So this is the impedance ratio between the secondary, the transformer, and then the load resistor. Okay, so in the DC load line, you can see it's a little bit similar to the series fit. If we put the amplifier in the class A, so we put the operating point over there in the middle of the load line, and then the saturation point or IC max. This is the AC load line, so this is the R accent L because this the transformation impedance in the transformer. So this is the load line. This is the load line, and then we can see that the IC max is at VCC per R accent L, and then the cutoff point is at the V2 or the secondary voltage of the transformer. So because of we can change the IC max to VCC per R accent L, and also the cutoff point to the V2 secondary voltage, it will be increase the maximum swing. So it will be increase the maximum output swing, because the minimum and the maximum value of the IC and VCE is spread farther apart. So it's like we increase there, over there, and then we increase there, like this one. So if we increase to the VCA to the right side and then the IEC to the upper side, so the output swing will be increased. If the output swing will be increased, on the output voltage will increase too. Not only the output voltage, but also the collector current signal. Okay. So this is the reason why if we use the transformer, it will be, the efficiency will be increased because of the output voltage swing, and also the current output swing increase, but the input is similar, is the same, so the efficiency will be increased. And then this is the signal swing and the output AC power. So the VCC peak to peak is equal to VC max per VC max min minus VCE min. Okay. Then the current swing is IC max minus IC min. So the AC power, the output AC is equal to VCC peak to peak multiplied by the current swing. So VCC peak to peak is here, and then the current swing is here per 8. Okay, so and then the input power is the DC. So we got that PI input DC is VCC.ICQ, and then the power dissipated as a heat of the transistor or PQ is PIDC minus POAC. And then we can get the maximum efficiency, percent efficiency is this one. Okay, so if we have so from the transformer, the maximum efficiency is 50 multiplied by VC max minus VCE min per VC max plus VCE min quadrat. So if the VC max, we have the larger VCE max, and this is larger, and then this is the smaller, so the efficiency close to the theoretical maximum is 50%. Okay, then this is the example. They calculate the AC power delivered to the 8 speaker from the circuit of the figure. The circuit component value result in a DC base current of 6 milliampere, and then the input signal VI results in a peak base current swing of 4 milliampere. So this is the IBDC is 6 milliampere, and then the input signal is the peak base current is 4 milliampere, and then this is the load, the AV characteristic, and then this is the circuits. Okay, so the first one, from the circuit we know that the VCC is 10 volt here. So the VCQ is equal to VCC is 10 volt here. So over there, this is the 10 volt, and then for the IB is equal to 6 milliampere because the base current is 6 milliampere. This is the 6 milliampere. So this is the ICQ. The ICQ in the y-axis is equal to 140 milliampere, and then the VCEQ is equal to VCC is 10 volts. Okay, then we can calculate the effective AC resistance seen at the primary transformer is Rxn(L) is equal to N1 per N2 quadrat dot RL. So this one, N1 per N2 is 3 compared to 1, 3 per 1. So N2 is 3 quadrat dot 8, so we can get 72 ohm. And then because of the Rxn(L) is 72 ohm, so it will be the AC load line can be drawn of slope 1 per 72. So because of if we didn't use the transformer, so the load line is the ideal load line. So if we use the transformer, so the slope will be changed, depends on what is the value of the R accent L. In this case, R accent L is 72 ohm, so the load line will draw a slope of 1.72. So then we can calculate the IC. IC is VCE per R accent L, so we could get 10 volt per 72 ohm. So we can get 139 milliampere. Then we notice that the IC is 140 milliampere plus the IC. The IC is 139. So this one. So this one is 140. We have the IC is 139. So we can multiply to the 140, and we can get the value of 279 milliampere along the y-axis. Okay, so 279 like this one here. Then we connect the point A to the operating point here, to the operating point, and we can get this one. And then we can calculate the VCE mean over there. This IB is equal to 2 milliampere because of below 2 milliampere is cut off. So the swing is between the VCE mean 1.7, because this one is here. The load line with the IV characteristic is have the cross section here, and then also with the minimum base current over there. So we can get VCE max is 18.3 and VCE min is 1.7 volt, and also the IC min is 25 milliohm, and IC max is here over there. Cross section here is 255 milliampere. So from this point, we can calculate the AC power delivered to the load. If the POAC is VCE max min VCE min multiplied by IC max minus IC min per 8, so we can get the 0.477 watts. And then we can calculate the efficiency. The first one, we have the input DC is VCC.ICQ. The VCC is 10 volt over there, and then ICQ over there is 140 milliampere DC. So we can calculate the PIDC is 1.4 watts, and then we calculate if we want to calculate the power dissipated by transistor, PQ is equal to this one, PIDC minus POAC. So 1.4 watt minus 0.77 watt over there, so we can get 0.92 watts. And then how about the efficiency amplifier, POAC here, per PIDC? So we can calculate percent efficiency is POAC per PIDC multiplied by 100%. So we put the value, and then we get the efficiency is 34.1%. So I think this is the example, and the clear. I think this is the clear example for the class A amplifier with the transformer couple for the part 2 power amplifier. So I think this is enough for the part 2. Thank you very much. Good morning. Assalamualaikum warahmatullahi wabarakatuh.